Sir, good afternoon, Dr. Vijay Kumar. Dr. Vijay Kumar, are you able to hear my voice, sir?
Yeah. I'm able to hear you. Am I audible, sir?
Yes, sir, you are audible.
Okay. Thank you.
Shall we start, sir? Can I introduce the presenter?
Yeah.
Yeah, good afternoon. This is Dr. K. Ramchandra Rao. I am very privileged to welcome you all to the second session of the FDP Recent Advances in Artificial Intelligence and Robotics. For this session, I am very extremely privileged to introduce session resource person, Dr. Vijay Kumar Dalla, and presently he is working as an assistant professor, Mechanical Engineering Department, NIT-Jamshedpur. He has completed his PhD in robotics at IIT Roorkee in 2016, MTech in Material Science, IIT Mumbai 2008, and he has his BTech in Mechanical Engineering from Government Engineering College, Bilaspur, Guru Ghadas University. His PhD title was Strategies for Control of Multiple and Hyper-Redundant Space Robotics under the guidance of Professor P.M. Pathak, Mechanical and Industrial Engineering Department, IIT Roorkee. He has around 18 publications as part of his research. Prior to his work experience as assistant professor in NIT Jamshedpur, he has working experience at Vijay Institute of Technology, Hyderabad, Ajay Kumar Garg Engineering College, Ghaziabad, RSR College of Engineering and Technology, Bhilai, and Guru Gohasi Das Vidyalaya, Central University of Bilaspur. And he was as senior research fellow at Industrial Research and Consultancy Service at IIT Bombay. He has taken up 2 projects, and he also worked as a teaching assistant during his MTech at IIT Madras and teaching assistant during his PhD at IIT Roorkee Mechanical Engineering Department during 2012 to 2016. He has research projects around 70 lakhs with 2 titles. One was Design and Development of Humanoid Robo 1.0 for various services uh, from the funding agency Drishti, and Design and Development of Extensive Flexible Robot for Underwater Inspections from IIT Indore. Presently, he is guiding 7 research scholars. Beyond his footprints in academics and research, he has administrative responsibilities like he is a member of Technical Committee of Convocation 2020, member of Central Committee of Student Activities, Policy Decisions, and member of Academic Committee for UG PG Research Program, and member of Research Consultancy 1920. And he has a very good sports background, where due to his sports background in badminton, football and hockey, he is now taking up as a professor in charge for Institute Sports and Athletics of NIT Jamshedpur and convener for Purchase Committee Goods and Services of Institute Sports and Athletics. And he has around 32 invited talks in various FDPs, and he has organized 6 short-term courses, and in this pandemic, he has completed 6 FTPs and short-term trainings. And as part of his research as a reviewer, he has been a reviewer for proceedings of institutions of mechanical engineering, Journal of Aeroscience Engineering, SAGE publications, Hindley publications, Proceedings of Institute of Mechanical Engineering Part 1, and Advances in Robotics elsewhere. And he is a member, permanent member for professional bodies as life member of Association of Mechanics and Mechanism and Robotics Society. So this is all from his profile. I'm very fortunate to introduce our resource person, and we are eagerly waiting for your talk on robotics of AI solutions to COVID-19. Thank you, sir. Welcome.
Yeah. Yeah. So, firstly, very much thank you, sir, for giving a nice introduction about me. So, thank you, Dr. K. Ramachandra Rao,
Thank you,
and HOD sir, Dr. P. Kiran Sri, for giving this opportunity to interact with the participants. So, once again, thank you to your institute, Sri Vishnu Engineering College for Women. And now I'm going to share my PPT. Yeah, please let me know if it is visible or not. I have
No.
shared my screen.
Yeah, now it is visible, sir.
Yeah,
It's a PDF file.
yeah. So as I'm going to talk in as a part of online AICT sponsored FDP on recent advancements in artificial intelligence and robotics at Sri Vishnu Engineering College for Women, Bhimavaram, AP. So as I requested yesterday, as I have given my topic, robotics and AI solutions to COVID-19 out of 7 topics, but it was approved. So, and in this, I want to add robo analyzer. Then I will come to the robotics and AI solutions. And the solutions means what are the options to minimize the outbreak of the COVID-19. It's not like solutions like coronil. Okay, so it's, the solution means not the complete solution to combat with the COVID-19. Okay, so in robo analyzer, it is a software 3D model. Based on that, we will visualize kinematics, dynamics of the robots. Okay, and I have seen the list of topics covered by the different reputed experts. So then I thought, why not to include this? Okay. So regarding this software, now why not to open that software? Then I will discuss all those things. Okay. So anyone can download the software. I'm going to open the Google, okay, and going to type Robo Analyzer. Personally, I found this software very nice for the understanding, for the visualizations of the robots, okay, for the visualizations of kinematics and dynamics, okay, and it is developed by IIT Delhi in the leadership of Professor S.K. Saha and his team. And yeah, if You can see this Robo Analyzer is a 3D model based software that can be used to teach and learn the robotics concepts. Okay. So as robotics is interdisciplinary, so it is not only limited to only mechanical people. Okay. So these are the little bit descriptions about the software. Okay, and it is a priceless software anyone can download. Okay, so from where we need to download? So if you see the left side, okay, there are the robo analyzer, then logo, then home, about, uh, downloads. Okay, so see in this download, what are the system requirements? Okay, for that computer, laptops are required. In mobile, you cannot. Okay, and if you see, there are the number of versions starting from Robo Analyzer V1 in a very starting days. Now, the latest version is Robo Analyzer V7.5. Okay, and if you see the right side, new features. Okay, so by the time being, in the every version, some new features are added. Like if you see forward kinematics of revolute joints, animation, graph, plot. Okay, so what about in the next version? Okay, see in the next version, forward kinematic of revolute and prismatic joints. Okay, earlier it was limited to only revolute joints. Now, then the later version, prismatic joints. And also one can visualize the DH parameters. Okay. And similarly, in the latest version, if you compare the latest and just the previous, so in the latest version, the homogeneous transformation matrix module is added. Okay, but what was in the uh, last version, add robot of any degree of freedom, new interface to add robot. Okay, it was added in the last version, means it is not limited to only what are the by default robots are there. Only we can visualize. You can make your robot. Okay, then you can visualize its motions. Okay, so this you can download it. Okay, from this link you can download it and you can have visualization. This I have downloaded. And now I'm going to access that to see Robo Analyzer. So see there are, if you see this screen, there are two applications. First one, Robo Analyzer STM module, and the second is the main software Robo Analyzer. Okay, this Robo Analyzer STM is just for you can say sub application. Okay, for understanding of transformations. Okay, so now I'm going to click. Okay, now see in the screen, two coordinate systems are displayed and both are coinciding to each other. Okay, the bigger one and the smaller one. And what are the axes? This red color denotes the x-axis, this green Y and blue Z axis. Okay, and what are the things like if you click the file, okay, so you can open new or you can open like this one, okay, you can access some file, okay, and this the transformation and sequences, okay, also you can sequence your motions, okay. What about this oh sorry, the visualization, so obviously it is the isometric view, okay. Also we can visualize the x y, the coordinate systems in x y, like this one, okay, x y or xz or yz. In this way we can visualize, okay. And I'm going to click the isometric view. The by default it displays, okay. Now the right side, if you see the local and a global, okay. Local means if see the smaller one, suppose it is the absolute frame, yeah, absolute coordinate system, which is also known as the fixed coordinate system, okay. And the bigger one, coordinate system, if we measure this, the bigger one with respect to the absolute frame, okay, then it will be known as the local coordinate system, okay. And suppose somewhere in the workspace, if you see my cursor movement, okay, so suppose any frame or any coordinate system is here, and which is the absolute coordinate system, and we are going to measure the coordinate system of the body, whether stationary or mobile. So if we measure with respect to that the coordinate system, then it will be known as the global coordinate system. Okay. So here what we are going to visualize, motions we are going to visualize. Okay. So transformations, in transformations we see the motion along the axis, motion about the axis, okay. So along the axis, if there will be translation along the axis, then that will be known as the pure translation, okay. And if there will be rotation about the axis without translation, then it will be known as the pure rotation transformation. If there will be both translation plus rotation, then it will be known as the combined transformations. Okay. So transformation means suppose whatever the things near about us, whether moving, suppose any moving of object. Okay. So what are the sequences for the motions? Like it got, suppose a robot got moved from one place to another, and that movement is only translation along the axis. And suppose after that it got rotated or taking a turn, okay, by some angle, okay. So these are known as the transformations. Okay. Now we are going to visualize the translation in x direction. Okay, I'm going to put any random values. Suppose I'm putting x is equal to 3, and now I'm going to click the translate. Okay, see the The smaller one coordinate system got moved along the x axis. Okay. Now resetting it, and same. Suppose we want to see along y direction, 5 units I have put. So see, it is the translation along the y axis. Now, same we want to see, we want to visualize along the z direction. Okay. Suppose I am putting any random value 4. Okay. So this is about the translations along the axis. Now again I am resetting it. Okay. Now suppose we want to visualize rotations. Okay. So here one thing to note that if we rotate any axis about its own axis, okay, then what about whether the rotation means if there will be rotation about its own axis, okay. So suppose we want to rotate about x-axis. So x-axis, you know, this red color, the bigger one and a smaller one axis. Okay. So both will coincide to each other or it will move. That is the main things we need to observe. Okay. And what about the other axis? They will remain at the same place or they will be rotated. So now I'm going to rotate about x-axis. Suppose angle I am going to give 60 degree. Okay. Now I'm going to rotate it. Okay. See. So what are the observations? Our observation is here. If there will be rotation about its own axis, okay, then there will be no movement in that axis. But the other axis like y and z got rotated. Okay, and another observation is it will be rotated by the same angle. Okay, this y rotated by 60 degree and this z axis rotated by 60 degree. Okay, and suppose this we want about y, this we want about z. Okay, and suppose we want again about the x-axis. Okay, and the x-axis, this the red color denotes the x-axis. So you can observe the rotations. Okay, again. So these are the sequences of the operations. Okay. Similarly, suppose we want to translate along the z-axis. Okay. And y-axis. So, in this way, okay, we can visualize. Okay. And what are the things? If you see the below matrix, the current matrix, show position, visualize. So it denotes the name itself, HTM, homogeneous transformation matrix. Okay, so matrix you all know. Matrix you all know here, but to get the solutions means to get the exact position and orientation of the robot and effector, we need to multiply the matrices of each transformation. Okay, getting my point? Each transformation will give one matrix. Okay, so all transformations, for all transformations, we need to multiply the matrices. Okay, then we can know about the exact locations of the AND effector. Whenever we are going to talk about a robot, we are going to, it means we are going to talk about the robot AND effectors. Okay, and what is that? The robot AND effector? The robot AND effector, which is means by name you can know the AND effector, the cause and effect. What are the causes? Due to input, torques, or the forces, the robot manipulator will move. Okay, robot manipulator will move, and ultimately its effect can be visualized at the end of the robot. That's why the name is AND effector. Okay, so through this matrix, at this stage we know for getting solution or to know about the location, we need to multiply all the transformations, means all the matrices. Okay, so what about this matrix and why it is known as the homogeneous? Why it is known as the homogeneous? Homogeneous means if you see number of elements in the row, number of elements in the column, so both should be matching. The same number of elements should be in both, either in the row or the column. Like if you see in this is row wise we are seeing 1, 2, 3, 4. 4 elements in the row, all the rows. Okay. And what about column wise? 1, 2, 3, 4. Okay. Means its dimensions are matching. Okay. Then only we can get solution by multiplying the matrices of same dimensions. Okay. Like square. If all matrices are in the square, then we can multiply the matrices, then we can know about the exact location of the robot. Okay. So that is the homogeneous transformation matrix. Okay. And the homogeneous transformation matrix, it denotes about the robot and effector. If you see the fourth column, so in the fourth column, first element denotes the X position, then just below one Y, and just below one Z. And this middle one, 3 by 3 matrix. Okay. Don't count the fourth number of rows. Okay. Leave the fourth column and the fourth rows. So what are the remaining? That is known as the rotation matrix. Okay. And if you see below, that sequence of transformations is given here like R1, R2, R3. Okay. Then T6, T7. Okay. Suppose one more we want. Okay. X2. Then till now T6, T7 is there. Now we observe T8, it added in the sequence of transformations. Okay, and it got moved. Okay, so the positions and the visualize. Okay, animation also we can do. See, these are the sequences of the transformations, and animation we can see what is happening, like 2, 3, what we did in the third step, and the fourth, 5, 6, 7, and the last one, that P denotes here translation. Okay, so in this way we can visualize the coordinate systems. Okay, and it is not only limited to robotics. For any things, okay, whether in the uh, computer science, electronics, okay, for any object which we are going to measure, location suppose we are going to measure, then we need to apply the coordinate system. Okay, it is not only limited to robotics. Yeah, please let me know if any doubts or if any queries you have. If you're allowed in the chat box. Okay, I think not allowed. Yeah, no problem. Okay. So this was about the HTM module, homogeneous transformation matrix module. Okay. Here we visualized about the movement of the coordinate systems. We know about the transformations. Okay. We know about the types of transformations like a pure translation, pure rotation, and the third one, rotation plus uh, translation. Okay. Also, we know about the local and the global coordinate systems. Okay. Also, we know about the transformation matrix. Okay. The transformation matrix denotes about both the robot and effector position and its orientation with respect to the base of the robot. Okay. Also, we visualized the sequence of the transformations. Okay. Now, I am going to open the another software, the main software. Okay. So by default, this robot named 2 degree of freedom, revolute joints. It is displaying. Okay. So see, this is the 3D model. Okay. The robot, the 3D model in this way, if you based on the cursor movement, we can zoom in and zoom out. Okay. So what about the coordinate systems? See, at all the joints, the coordinate systems are there. Okay. Then only we can locate the end effector. Without fixing the coordinate system, we cannot locate the end effector. We cannot locate the robot. Right? Okay, where is our robot? We cannot locate. Okay. Now, see, if you see below the DH parameters, okay, whether you're from mechanical, CAS, electronics, okay, it is a very general question, DH parameters. So what is this DH parameters? And what is this DH convention and why it is required to study? Okay. For the simple robot, easily you can locate the position and the orientations. Like this kind of robot I have shown here, anyone can locate. If suppose you want to know about the robot and effector position, okay. So what you have to do? If L1, L2, L1, this will be L2. Okay. So what will be? With the help of, now I'm going to open my PPT for this. Okay. Simply, if you see this one, this kind of robot, it is a very simple robot, serial manipulator. Why serial manipulator? Because the links are connected in a series, one by one, and joints are there to provide relative motions, okay, to the links. Okay, so for this kind of robot, easily you can get the robot and effector positions like XE, YE, or phi E. It denotes the orientation. Okay, so what we have to do? Along the x-axis, we have to measure. Okay, like for this link one, what you need to do? You need to write this equation. It is for the y direction. Okay, so what will be YE? You can see YE will be L1. Okay, what we are going to be means this, we are going to this height from the origin we want to know. Okay, in the second step, this height from here origin, and in the third stage, this we want to know. Okay, so this can be written very easily. You can see L1 sin theta 1, okay, plus L2 sin theta 1 plus theta 2 plus L3 sin theta 1 plus theta 2 plus theta 3. Okay, so why I'm saying this, for this kind of robot, easily we can get the robot and effectors, positions, orientations, but in the case of difficult robot, we cannot locate the robot positions, orientations. Okay, so in that case, what we need to do? Then we need to take help of DH convention. Okay, by using this convention, very complex kind of robots can be located, like a cooker robot ho gaya, okay, and suppose a robot having x, y, z axis, okay, and there may be some prismatic kind of joints, revolute kind of joints, okay, some spherical kind of joints. Then how to know the robot and effector location will be difficult. Okay, but using this DH convention, we can easily get. Okay, so this DH convention, what is the full form of DH? Dana-Wade Hartenberg, named after two scientists, Dana-Wade Hartenberg. Okay, and what are the parameters? So there are four parameters. If you see the screen, joint offset, joint angle, link length, twist angle. Okay, so these can be easily understood. Joint offset in the case of prismatic joint. Okay, the variable is known as the variable is known as the joint offset. Okay, and suppose if there will be rotary or revolute kind of joints, okay, then the joint variable will be known as the joint angle. Okay, what about link length? If you see this robot, okay, and the link between the joints, that is the link length. Okay, and what about the twist angle? If you see in this twist angles are 0. You can see twist angles are 0. Okay, so you can see this z axis. So these z axis are both are parallel. Okay, like if you see my hands, if two axes are not meeting at any point, means both are parallel, okay, then there will be twist angle will be 0. If both are intersecting by some angle, okay, then there will be some values. Okay, so there are 4 parameters: joint offset, joint angle, link length, and twist angle. Okay, so now I'm clicking the base frame to end effector. What is the base frame? This the frame means the coordinate system attached at the base of the robot. Okay, so this the where the link starts is known as the base frame. Okay, here now I'm going to click this base frame to end effector, then see what is happening. And yeah, see, the 3D model and the simultaneously see the DH parameter table. Okay, again, see, if I click this base frame to end effector, what is happening? Joint number 1, revolute joint, and now it is coming to joint number 2, and the joint offset is 0. Okay, and joint angle is variable here, and the link length 0.2. 0.2 it got translated. Okay, twist angle is 0. Okay, now the initial value and the final value. The initial value is what? The position of the robot. The final value is what? The final position of the value. Okay. Okay. So now here there are number of default robots like 1 degree of freedom robot, 2 degree of freedom robot, 3, 4, 5, 6 degree of freedom robot. Also we can visualize. Okay, this is the 6 degrees of freedom robot. Okay, and 4 degrees of freedom robots. Okay, and this 2 degree of freedom robot revolute joints we have visualized. Okay, what about the prismatic joints? Okay, if you click and select 2P, okay, and click load selected robot, okay, means it will take updates. Okay. See what is happening here. It got updated and the joints are now the prismatic joints. Okay. Base frame to end effector. Now I'm going to move the coordinate systems. Okay, and what's happening? You can see here. Okay. Now, the forward kinematics we want. What is the forward kinematics? Okay. For better understanding, why not to select some more robot and revolve joints. Okay. This one. Now, there are four things: forward kinematics, inverse dynamics, forward dynamics. Okay. In the case of forward kinematics, what we want to know? We want to know about the robot and effector location. Forward kinematic. In inverse kinematic, what we just reverse it. Now we want to know about the joint variables. Okay. So forward kinematics, what we want to know once again, we want to know about the robot and effector positions. Okay. Now I'm going to play it. Okay. See what's happening. Okay. And this traced solid curve is known as the trajectory. Okay. The trajectory is the time varying path equation. It depends upon time. If you read in some books, it is clearly defined the difference between the path and the trajectory. The path is the time independent equation of the you can say robot trajectory. Robot means it's a time independent equation. Okay, but the trajectory is the time varying equation. Okay. Now, the forward kinematics, what we are going to know and what are the inputs. So joint angles were the joint variables. I'm not saying joint angles because there may be also prismatic joints. Okay. So joint variables are the inputs. Okay. And what are the outputs? Outputs are here to know about X, Y, Z. Okay. These are the outputs. Now, inverse kinematics. In inverse kinematics, the outputs will be now inputs. Okay. You can see here the end effector's position. X is equal to 0.35 meter, Y 0.1, Z 0.5. Okay. So these are the fixed now. And what are the variables, the joint variables that we want to know? For the given end effectors positions, what will be the state of joint angles? Okay. So now I'm going to click the inverse kinematics. Now see the solutions. Means to reach the same goal point, what are the alternative options we have? Like so, and that is known as the solution 1, solution 2, 3, 4, and so on. 8 solutions are displayed here. Okay, there may be more solutions, but due to this software constraint, it is displayed only 8 solutions. Okay, means 8 there are multiple ways to reach the same goal point for the given inputs. Okay, and what are the inputs? The joint offsets, link length, twist angle. These are the inputs. Okay, and the number of solutions depends upon these inputs. Okay, so at this stage we know about the forward kinematics, then inverse kinematics. Forward kinematics gives only one solution. Inverse kinematics gives the multiple solutions. Okay, and sometimes single solution. Sometimes no solution. Okay, suppose a robot is going to dealt. Okay, robot is going to suppose pick water bottle. Okay, and that is beyond the reach of the workspace. Wonder what is the workspace? Workspace is the maximum reach of the manipulator. Then do we have any solution? No, because the object is not inside the workspace. Okay, so in inverse kinematics, we get either single solutions, multiple solutions, or even no solutions. Okay, so inverse kinematics. Okay, now if you observe, suppose I am going to click solution 1. Okay, what is happening? See, solution 1 I have clicked. Okay, so solution suppose 4. Okay, solution 5, 8. Okay, so what is happening? The robot configurations are being changed, but the end effector positions are at the same point. Okay, you can further visualize. I am going to click the solution 1, solution 2, solution 3, solution 4, solution 7, and so on. Okay, so with this, please allow me for a 2 minutes break. Then I will come back. Yeah, please allow me 2 minutes break. Hello. Hello.
Yes, sir. You are audible.
Yeah, am I audible, sir?
Yes, sir.
Yeah, yeah. So in this way, we can visualize a forward kinematics, inverse kinematics, even dynamics, like forward dynamics and inverse dynamics. Okay. So for visualizing dynamics, we need to take help of graph, because there will be the motions will be same, only the extra part will be added, means that will be information about the forces, torques. Okay, so that I'm going to do. Okay, forward kinematics, then see, suppose we want to know about force and torque. Oh, doesn't exist. Okay, showing doesn't exist. Okay, so what we have to do? Okay, see the motion, and I'm going to click graph. Okay, data doesn't exist. What about the other things? In this way, we can get the robot and effector positions. Okay. Okay. Now, suppose we want to for this kind of robot. Okay. So this I am doing. Then okay. Oh, what is happening? Yeah, no dynamics now. Yeah, now. So in this way, we can visualize the forces and the torques by the help of graphs. Okay, but the robot motion will be what we are seeing will be same. Okay, whether we include the dynamic portions or not here. Okay, in this way we can visualize the kinematics and the dynamics of a robot. Okay. Now I'm coming to the PPT part. So there were some assumptions, kinematic chains, then forward kinematics and the inverse kinematic. This we came to know about. Then how to means know the positions and the orientation of this kind of simple robot. Okay, and inverse kinematics. So what are the problems with the inverse kinematics? Okay, so sometimes the problem is sometimes we don't get any solution. Okay, but what are the plus things? We get multiple solutions. Okay, and these are some assumptions, and the multiple solutions again. See, to reach the same goal point, there are two configurations: elbow up and the elbow down. Okay, so in this way we can reach the same goal point by the two ways. Okay, same here, using these parallel linkages also we can understand. Okay, and regarding DH conventions, these are the regarding DH convention, DH parameters. Okay, and by with the help of DH convention, how we can get the uh, to know about the parameters. So for the simple robot, also we can go with the DH parameters, but which is not advisable. Okay, for the simple robot, you opt only geometric analysis. Okay, simply we can get. Okay, so regarding this robo analyzer, so what we came to know about homogeneous transformations, DH parameters, forward, inverse kinematics, and motion planning. Okay, and it is very useful for the uh, robotics education. Okay, theory plus if suppose we don't have any actual robot. Okay, so we can visualize, we can for practical purpose we can model the CAD and simulate real robots. Okay, like we have feeling like a real robots. So okay, these are the some things which I have already covered. So the robo analyzer software. Okay, transformations. Okay, now I'm coming to the robotics and AI solutions to COVID-19. Okay, so my request is here not to see like complete solution, to see like just alternatives to break the spread or outbreak of the COVID-19. Okay, so companies all around the world are exploring ways to use robots to increase and maintain social distancing. Robots are performing the jobs that workers are unable to play from home. Okay, it is very obvious. The biggest retailer in America, Walmart, is employing robots to clean its surface. In South Korea, robots have been used to take temperature measurements, and the machines are under used by restaurants and the grocery. Okay, these are the in this way the robots are being used with the help of artificial intelligence. Okay, so from internet source I came to know there are 10 ways. Okay, robot fight against the COVID-19 pandemic. Okay, the novel coronavirus crisis has increased the public interest in the robotic technologies and artificial intelligence. Okay, and seen as effective resources in combating the pandemic. Okay, let us check some examples of how robots are addressing the challenges posed by COVID-19. Okay, in Europe. Okay, so inside the hospitals, robots can be deployed for disinfection, medicine, food delivery, vital signs of monitoring, thus helping to significantly reduce the infection risk of all populations. Okay. What are the ways to fight against COVID-19? Okay, so like it can disinfect hospital, deliver medicines, blood tests. It can do food and help with the hospital logistics in the general. Okay, robot help keep doctors safe from coronavirus. It helps speed up the coronavirus tests. Robot help for patients and the elderly to maintain social distance. In Spain, ABB robots have been reprogrammed by Nagami, designed to produce Yeah, sorry for the disturbances. Okay. So, what about made in India robots and how these robots are helping health workers to fight COVID-19? Okay. So, see Astra, Mitra, and Robodog by Invento Robotics. Bangalore-based Invento Robotics, founded by Balaji Viswanathan.
Can
Okay,
you share
and
the PPT, sir?
yeah, yeah, yeah. Okay. Now we are going to talk about made in India robots. Okay. So C Astra Mitra Robodog by Invento Robotics, Bangalore based Invento Robotics, founded by Balaji and his group. Okay. And it is full stack robotics startup that helps automate customer engagement in banks, airports, restaurants, and other places. The startup has now turned its business focus to help fight the coronavirus pandemic. Okay, so the robot, the picture is not clear. Okay, he's a founder Balaji Viswanathan. Okay, co-founder Invento Robotics, and the source is given here. The link is given here. He is with his own made robots. Okay, for COVID-19. Okay. So Mitra, which was designed for customer engagement and alert host about the arrival of visitors. Okay. Likewise, I'm not going to detail all those things. Okay. So if you see, while C Astra and the Mitra can be used in various sectors, including shopping malls, metros, warehouses. Okay. But the RoboDoc is especially designed for the healthcare sector. Okay. There are also some startup companies, Milagro Human Tech, founded by Raju Kanwal. Okay. In 2007, recently he launched 4 new humanoid robots. Humanoid robots means it looks like human, and these are the name of the robots: Robo DiCaprio, Robo Julia, Robo Namo, Robo L. Okay, it is specially designed to cater to hotels, hospitals, restaurants, and corporate offices. These humanoid can interact with the customers. Okay, this we all aware nowadays. It can interact with the customers. You might be knowing about a Sophia robot. Okay, Sophia is a humanoid robot and can interact, can answer, can reply, can show emotions. It can be anger. Okay, and also Esimo Robotics. Okay, based at Kochi. So Esimo Robotics under the Kerala Startup Mission developed 2 humanoid robots in March this year. Okay. These robots were the first in the country to raise the awareness about the spread of coronavirus among people in Kerala. The robots currently distribute masks, sanitizers, and napkins in the startup. Okay, so and the robot named Prithvi by Delhi teenagers. A group of teenagers from Delhi had built a robot called Prithvi to protect the healthcare worker by reducing their contact. Okay. And there are many startup companies, they are making a robot, okay, to ultimately to break the chain of transmission of COVID-19 with the help of artificial intelligence. Okay, that's why these are only application based. Okay, and if I totally discuss with application based, so it may be boring. That's why I started with the robo analyzer. Okay, and now we want to see some because the institute is located at Andhra Pradesh. So why not to see some examples? Okay, what are the things? Means what are the developments in the Andhra Pradesh? So you can see the COVID-19 robot to assist doctors at Nellore Government Hospital. Okay, so it is being used in Nellore. And what about this robot to solve COVID-19 patients in Andhra Pradesh, Vijay? And that Sophia robot was invited in some tech festival, Vijay Tech Festival in Vijay. In sorry, Vijay it was invited. Yeah. So see the named made robot, the device has been put into service from the, yeah. So this is the robot. Okay. And the Visakhapatnam based Volunteer Division of East Coast Railway has developed a fabricated robot to assist hospital staff to serve COVID-19 patients. Right? Okay. Named as Made Robo, the device has been put into the service from Tuesday. Okay. Based on this news. Okay. So there are many applications of the robots in the field of COVID-19 and Andhra Pradesh. That's why I searched. The institute is located in the Andhra Pradesh. So why not to search some developments? So there are many developments. Okay, the Matri robot. Okay, in Vijayawada, Matri robot to serve COVID-19 patients in Vijayawada. Okay, you can see the robot with the concerned persons. Okay. And why not to see some examples? Okay. I'm going to play. Okay. These are the robots, recent developments to fight with the COVID-19. Yeah, we need to skip this. Just taking time. Okay, so there are many examples. Now, almost I have completed. Now I'm going to share. Yeah, I'm going to share this link. The link itself has 10 multiple questions. So if I think I'm not allowed to share. Yeah, how to share, sir?
So you can send it to the convener, sir. He will share to the participants.
Okay. Okay.
Professor,
That I'm going to,
yeah.
that I'm going to share. Yeah, I have shared, sir.
Thank you, sir.
Yeah, this you can share to the participants.
Sure.
It is based on my today's lecture. Okay. So with this said, thank you. And
Yes.
if participants have any queries, they may interact with me.
If any questions, please unmute yourself and ask the resource person. If not, we can close.
Participants, if you have any questions, you can unmute your mic and you can ask the resource person.
Okay, sir. If not, we can conclude the session, sir. Thank you, Professor Vijay Dalla. And you have enlightened us with your talk on robo-analyzer, isometric visualizations, matrix, homogeneous matrix and modules, sequence animations, 3D coordinate system, DH conversions, and forward and inverse kinematics, and robots in COVID-19 abroad and India. That is all. Thank you, sir. Thank you very much.
Yeah.
Thank you for joining FTP. So we can end up the session, sir. Thank you.
So participants, if you don't have any questions, so we'll wind up the session for forenoon. So we'll resume the session at 3 o'clock. So we have a section on stress management. Dr. Bhavani Prakash will grace the session. So the session will be started at 3 o'clock. Thank you, guys.
Thank you all. Let us join at 3 o'clock again. Thank you.